Hi, everybody, and welcome back. We are at the top of page 7 in our equilibrium notes. And right now we're getting ready to do some complex equilibrium problems. But don't worry, we have actually a very helpful method that we're going to use that will allow us to go through this process. Okay, so I have appropriately titled this section of our notes, Some Calculations with the Equilibrium Constant. So what we're going to do, we're going to set up these things called Rice tables. If you're looking online, oftentimes you'll see people call them ICE tables or ICE diagrams. We're going to go ahead and call them rice tables, okay, or rice diagram. One of the things that you have to understand is that each of the letters in rice stands for something that will help you, the learner, how to set up these problems. So let's take a look at R. R is going to stand for the balanced reaction, R meaning reaction. The I component in rice diagrams is going to represent, and consequently where you will write the initial I for initial concentrations. The C component in the rice diagram is the change in concentration. And by the way, we are going to set the change in concentrations in terms of X. Lastly, the E component or E portion of the rice table represents and stands for equilibrium concentrations, of course, in terms of X. So these rice diagrams are going to be used in calculating equilibrium problems. A couple of other things before we jump into some examples. And I will be honest with you, the wording here might confuse you, and in many cases, it's just easier to dive in and show you practice problems and examples, and then coming back to the words that are written would make more sense. But nonetheless, here they are, so let's go through them. We're on number 2. So after you set up your rice table, you are going to set up the equilibrium expression. Okay, so next to your table, you can write the actual equilibrium expression, which we did learn how to do in the first part of this unit. And what you're going to do is you're going to set it equal to a value. Of course, if that value is given, it may not be. Step 3, you should celebrate if the problem actually gives you the equilibrium concentrations. That's going to it's going to simplify your calculations, at which point you will just go down to the E portion of your rice table and literally fill it in, okay? Sometimes you might be asked to work backwards to determine the change in equilibrium, but sometimes maybe not. Okay, and then the fourth thing on here is if you are given a K value, so if it happens to give you the K value in the problem, then you're going to use it to solve for X, and then you're going to use X to calculate the equilibrium concentrations. Again, if any of this is confusing you, we're getting ready to work some problems, so hang tight. A couple of other bullet points here. Look for very small values of K. You can see where I mentioned K would be less than 10 to the negative fifth. That's because X then at that point may be negligible. All right. Second bullet point, that if X is large enough to impact the equilibrium values, then you must subtract it from the initial concentration. Your math will be simplified if the problem is a perfect square. If not, you're going to use the quadratic formula. Okay, so really quick, we probably remember what the quadratic formula is. In case you didn't, it's the X equals, and this is from algebra, so for some of you it's been maybe a while. You might want to write this down and just jot it down to familiarize yourself or refamiliarize yourself with it. Okay, here's the quadratic formula. Now here's the thing, that can be a real pain in the butt to enter into your calculator. So what I really want you to do, and I made a separate video on this, is you should pre-program any fundamental or important formulas that you're consistently using in chemistry or any math class for that matter. When you hit the program button on your graphing calculator, at least for a Texas Instrument, my option number 1 here is where I have pre-programmed my calculator with a quadratic formula. You should definitely do that. Again, it saves you time and it reduces error. So you go ahead and watch the video, pause right now if you haven't done that, and do so before moving on. Okay, one of the last things, the last bullet point here before we jump into exercise number 8 is if none of the initial concentrations given to you in the problem are 0, okay? If none of the initial concentrations are 0, then you actually have to calculate Q first. Remember, we covered Q in the last video. So if you jumped ahead, or you can't remember, or you need a review, it might be worth it for you to go back and remember what the reaction quotient means, how to calculate it, but most importantly, also when you use it and when to do Q, when to calculate it, okay? When you do calculate Q, remember, ultimately, you're always going to be comparing it with some given value of K. Okay, and once you do the comparison between Q and K, you are then going to need to make a judgment call. Does this particular reaction need to just keep trudging forward to create more products? Or does this reaction already have way too many products? And that's because my Q would be greater than 1, right? In which case, if that's the case, it's going to reverse it's going to need to be reversed and send it back in the other direction. So know what Q means, okay, you guys? Now let's just go ahead and jump in. Again, sometimes if you're lost, or if you are lost at this point, it might just be easier to do practice problems. All right, exercise number 8. It says, dinitrogen tetraoxide in its liquid state was used as one of the fuels on the lunar lander for the NASA Apollo missions. In the gas phase, it's going to decompose to gaseous nitrogen dioxide, and you can see the balanced reaction right there. It then goes on to say, consider an experiment in which gaseous N2O4, dinitrogen tetraoxide, was placed in a flask and allowed to reach equilibrium at a temperature where Kp equals 0.133. At equilibrium, the pressure of dinitrogen tetraoxide was found to be 2.71 atmospheres. Calculate the equilibrium pressures of the product, which is nitrogen dioxide. All right, you guys, here's where you should celebrate, because look at it, says at equilibrium, the pressure was found to be 2.71. When you see the word at equilibrium, you should definitely celebrate, because the problem is actually going to be a little bit easier. And actually, in this particular exercise, we do not need to set up a rice table. Okay, so let's go ahead and lay this out step by step. Right off the bat, we know if you go look at the balanced chemical equation, it is a 1 to 2 mole ratio. Now, you guys, calculating that delta N, we don't necessarily need it for this particular problem, but it's really good to always do this, because sometimes you might need it. Remember what delta N was. 2 minus 1, where the 2 and the 1 are the molar coefficients of the balanced chemical equation. So our delta N for this reaction is a +1. All right, so let's go ahead, and I noticed that they gave me the Kp is 0.133. And in this particular case, if you're always confused, first thing you should do is always write the equilibrium expression. And so we know that the equilibrium expression would be Kp, and then it would be products as in our numerator raised to the exponent of our coefficient. And then here is our denominator. Okay. And in this particular case, it actually probably would be more appropriate, seeing how these are gases, to write the equilibrium expression in this version. There we go. And we do know that we know Kp, it was given to us 0.133. And it's asking us to calculate the equilibrium pressure of NO2. So not only were we given the Kp, the equilibrium constant for this particular reaction, if you go and look back into the problem, it gave us the pressure at equilibrium of the reactant, dinitrogen tetraoxide, and that was 2.71 atmospheres. Okay, again, we do not, one more time, you guys, we don't need to set up a rice table for this. It seems like I'm just going to be solving for the numerator of this expression. So this is basically what I'll be solving for. I think that we can all agree that's exactly the givens that we have. So we're going to rearrange this equation to get the pressure of nitrogen dioxide by itself. So you would end up getting, remember, in terms of back in algebra, what we would do to get that squared away from NO2, you would definitely get rid of the square by taking the square root of both sides. So if I were to go back and rewrite this, it would be PnO2 equals the square root of 0.133 times 2.71 atmospheres. Okay, so if we go back to our calculator, I look at the values that were given to me within the problem, and I see that I should probably be reporting this to 3 sig figs. So the equilibrium concentration of nitrogen dioxide would be 0.600 atmospheres. And you can see that it aligns with the answer given at the bottom of the box. All right, so that one was our easier one. For exercise 9, we are going to set up and get ready to do a rice table. If you saw this in honors chemistry a couple of years back, then good. That's awesome. And for those of you who can't remember it or have not seen this, just go with me and be sure to compile any questions that you have and write those down so you don't forget them. Okay, top of page 8, exercise 9. Here we're going to go ahead and break out the rice table this time. One thing that you guys need to be completely solid on as a quick reminder, and I'm sure you know, that when we talk about concentration, which oftentimes we represent using brackets, of course, we know that that means molarity. You need to understand that when we set up these rice diagrams, we're really talking about concentration here. Now, one of the things regarding concentration of substances of gas is sometimes we might be talking about partial pressures. If you take a look at this problem, you don't see anything about atmospheres. I see moles and I see a volume. I'm just kind of glancing over with my eyes. Don't worry, we'll read the problem here in a minute. So we're dealing with concentrations here. All right, so it says at a certain temperature, we got a 1 liter flask that contains 0.298 moles of PCl3 and 8.7 times 10 to the minus 3 moles of PCl5. After the system has reached equilibrium, we then have 2.0 times 10 to the minus 3 moles of chlorine gas found in this flask. Gaseous PCl5 decomposes according to this reaction. And you can see that the reaction is given to you and it is balanced. It then goes on to tell us, and this is kind of what to watch out for in terms of the wording and kind of knowing what you need to do, what you're being asked. We're being asked to calculate the equilibrium concentrations and the value of K. So first thing is first, before we even set up our rice tables, over to the side, I want you guys just to write the equilibrium expression. We don't have equilibrium concentrations right now, so you would just write the general expression. So at the end of the day, you guys, we need to figure out what the equilibrium concentrations are of everything, plug it into the equilibrium expression to solve for K, to get the value of K. So in this particular case, you are going to be setting up a rice diagram. Don't forget R stands for writing the reaction. And they already did that for us. So I just kind of put an R off to the side. The next thing we're going to write is the initial concentrations. Then we're going to write the change in concentrations, and that will be in terms of X. And then we will write the equilibrium concentrations in terms of E. So give yourself a little bit of space. I'm going to go ahead and write and kind of break out my diagram. Okay. Now, here's the thing, you guys. You probably don't know why I did 3 columns. Well, that's because in the first column here, I'm going to put all the information with the reactant PCl5. In the second column, I'm going to put all the information for our product PCl3. And in the third column, you're going to put the information for chlorine, the other product produced in this reaction. So I set up my rice table, and I'm making sure that I have enough columns to accommodate all the species of the reaction. All right, so I is the initial concentration. Really quick, we're putting in concentration values. If you go back to the problem, let's go back up here. We are starting off with 0.298 moles of PCl3. Oh, hold on, here it is. 8.7 times 10 to the minus 3 moles. You guys know that these are happening in 1 liter flasks. So to get the concentration, to get the concentration of said things, for example, to get the concentration of PCl3, the initial concentration, you would just say 0.298 moles over 1 liter, which would then be 0.298 molarity. Okay, and then you would do the same thing for PCl5, and that would be our molarity. So these that I just calculated over to the right are the initial concentrations. and it says initially contained. So that's kind of your clue in there. So I'm going to go ahead and in this particular column, put in our molarity that I just calculated. Did they give us the initial concentration of chlorine? I keep reading the problem, and in the second sentence, they say that the system reached equilibrium, and oh my gosh, we had 2.00 times 10 to the 3 minus 3, moles of chlorine gas. You guys, is that an initial concentration? No, it is the concentration after equilibrium has been reached. We'll come back and see where we're going to plug that value in. But right now, they did not give us the initial concentration of chlorine gas. So therefore, you're just going to put a 0 there. Okay. Now we go down to the C part of our Rice diagram, and that stands for the change in concentration in terms of X. Okay, before we do anything else, remind yourself that the molar coefficients, the ratios here are a 1 to 1 to 1. When you get to the C portion of Rice diagrams, you have to respect the stoich, okay? So if you look at PCl5, there's a 1 there for our coefficient. So I'm going to do minus 1x. Now let's go ahead and jump over to the product side. I'm going to do a plus 1x for PCl3, and then I'm going to do a plus 1x for chlorine gas. Now you might be asking yourself, why the minuses and the pluses, and how do I know? Well, think about what's happening generally in a reaction. You're starting off with, assuming you're initially starting off with 100% of PCl5. Once the start of the reaction occurs, you assume that you're going to lose some of the PCl5 to form the two products. So we use minuses and pluses to represent that. So it's minus 1x for PCl5 because you're going to lose the reaction. And it's plus 1x for the two products because you're going to gain those particular products. Does that make sense? All right, so now what you're going to do, and one more thing before I move on, make sure you understand that these numbers, ones, are representative of the coefficients from the reaction, okay? Now, let's keep going. What you're going to do is go down the column of I and C, add these two terms together, and you're going to put that in your E column, which is your equilibrium concentration column. So in this particular one, for the first one, I would get, and I'm going to write this out of scientific notation, you guys. It's just easier because I don't have much space here. 0.0087 minus 1x. You're just going to combine the terms and follow it down. Again, let's go to the first product there, PCl3, and you would just take the I and C columns, combine them. So you're going to get 0.298 plus 1x. And then in the chlorine column, of course, you would just, again, do the same process. You would just get x or 1x or whatever. Again, you don't necessarily need to write the ones, you guys. It's implied. I'm just showing you that you have to still respect the stoichiometry when doing equilibrium calculations, okay? Now, what's interesting is we were hoping to get the equilibrium values, but we have the x variable we need to concern ourselves with. Now let's go back to the problem. Do you guys see right here where it tells us that chlorine had reached equilibrium, and when it did so, it was at 2.00 times 10 to the minus 3 moles. Well, you guys, that's happening in one liter flask. So you could easily find the concentration of chlorine. So that is our equilibrium concentration. So here's the thing. They basically gave us x. X is 0.002. And actually, they did. They gave us x in the problem. So now I have solved for x, you guys. It's 0.002. Just take this value and plug it into the x and the other two species in this reaction to get an actual value, okay? So for this one, you'd get 0.0087 times 1 times x, which we determined was 0.002. It's going to be 6.7 molarity. There you go. Again, we're talking in terms of concentrations here, so I slapped an M. All right, let's go ahead and do the calculations for PCl3. 0.298 plus 1.002. I think you get 3 molarity. And by the way, this one was M. Look at that, you guys. You now know the equilibrium concentrations for all the species in the chemical reaction. You are simply going to now plug these values into the equilibrium expression. This is a relatively easy calculation, and hopefully you were able to get the same answer I did, which I got 8.95 times 10 to the minus 2. Okay, so not only did we determine the equilibrium concentrations for all species, but we determined the K value. Let's take it a step further and do something a little bit more complex. Yep, we're still going to use rice diagrams, but this one you'll see each problem oftentimes gives you a different set of information, at which point that's when you will actually determine how to set up your rice diagrams. Carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. At 700 Kelvin, the equilibrium constant is 5.10. It's asking us to calculate the equilibrium concentrations of all the species of this reaction if 1 mole of each component is mixed in a 1 liter flask. So right off the bat, they basically gave us molarity. They gave us moles and the volume, and we just divide the two. You guys can see here it's going to be 1 molarity for all species. So let me just go ahead and write that. 1 for all. 1 molarity for all. But wait a minute, where's the balanced chemical reaction? Yeah, it's not here. So let's go ahead and write it. All right, you guys, does that look right? And go ahead and take a second. Does this equation look balanced? One of this, one of that, 2 hydrogens, 2. Okay, it looks balanced. So it looks like I'm going to have 1 coefficients in front of every species to get this to be balanced. Okay, so now let's go to the I part of our rice diagram. Remember, this is where you're putting initial concentrations. Where in the problem did they give us initial concentrations? Look at this last sentence. It wants us to calculate the equilibrium concentration if we begin with 1 molarity of everything. So they gave us the initial concentrations for everything, which are 1. And you guys can write 1m if labeling your units is important to you in these rice diagrams. For me, because we're solving for x, I tend to leave the units out of my rice diagrams, but make sure your final answers always have units, you guys. Okay, so there's our I. There's our initial concentrations. Now we're going to go to the change in concentrations. And by the way, you guys, how many columns are we going to have? We're going to have 1 for everything. So we're going to have 4. Let me go ahead and just draw this down a little bit more. We're going to put E here. There we go. I kind of just set up the rice diagram. All right, so remember, change in concentration in terms of X. Now, reactants, are they going to be minuses or pluses? Remember, you're going to lose the reactants. So here we're going to get a minus 1x. Minus 1x. Again, you don't need to write the ones. I'm just being detailed. And then your products, plus 1x, plus 1x. Okay, plus because we're gaining the products. Oh, really quick, I just don't want to lose sight of the fact that they did give us our equilibrium constant right here. So I know right now K equals 5.10. So I have my equilibrium constant value, so I'm keeping this in mind, all right? I recall too, at this point, we kind of need to figure out what's going to happen. So I'm going to stop here really quick, and I want to bring something to your attention. That if we're writing the equilibrium expression for this, and honestly, you guys, it's the first thing we should have done after we wrote the balanced chemical reaction. This is what you're going to get for your generic or your general equilibrium expression. So right now, we know that our initial concentrations are 1 molarity for each substance. Now, when you're saying you're doing the equilibrium constant, that's the value of this reaction at equilibrium. But initially, all the concentrations are 1. Right? So if you know right now, as it stands initially, when you use the initial concentrations, your K value would be 1. But the real K value at equilibrium is 5.0. So this is where you guys would set up the reaction quotient. So really, you guys know that Q in this case, which is 1, is less than K, which is 5.1. So because 1 is less than 5.1, I'm expecting that this reaction is going to shift to the right because our Q value is less than K. Okay? So you got to remember that, know that. So this is my pre-thinking over here to the side. Clearly this reaction is not at equilibrium, and that makes sense because they gave us initial concentrations and not equilibrium concentrations. Okay, so let's go back and finish the Rice diagram. Remember, you're just going to take the I and the C portions and then combine terms, add them together. Well, that doesn't really do us many good. We need to figure out what X is, right? Well, I'm going to do some writing down here in the space below and do these calculations, so hopefully you can see what's going on here. Well, if you guys know that the equilibrium expression, and I'm going to go ahead and highlight it over here to the right, I highlighted to the right the equilibrium, the general equilibrium expression. Well, if you know that, then wouldn't this be true? Okay. So 5.1 was our equilibrium constant. I got that from the problem. And now I'm setting up the expressions in terms of our equilibrium values that we got from the Rice table. Okay, if you guys actually remember some basic algebra, then wouldn't you agree this is true? Does that make sense? When I combine those two terms, I get 1 plus x squared divided by 1 minus x squared. Well, look at that. That looks like a perfect square. To get rid of those exponents, those squares, you got to take the square root. So if you don't mind, I'm just going to kind of show you. I'm going to take the square root of this guy. And what I do to one side of the equal sign, I have to do to the other. So don't forget the other side of the equal sign was 5.10. So I'm going to rewrite this, you guys. So 2.26 equals 1 plus x over 1 minus x. Do you guys see how we've simplified it this far? All right, we're trying to get x all by itself. That is our goal. Let's go ahead and get that denominator 1 minus x out of the way. So I'm going to go ahead and just rewrite that. I'm going to have 2.26 times 1 minus x equals 1 plus x. I'm going to tell you that you should get x equals 0.387. All right, well, now you have x. You just solved for x. Now you can go in and plug in that x value into the values of the E column in your Rice table. So look at you guys, you literally have solved the x values for each problem, you know the equilibrium concentrations for each species. All right, so that basically answers question 10. Okay, there's 2 more exercise problems here, exercise 11 and 12, that I think we're going to go ahead and do in class. Thank you so much for watching. Until next time, bye.